Iterations. As stated before, whenever dealing with a linearized problem, namely a non-linear problem that has been linearized by Taylor series expansion, iterations are required to obtain the best estimate. In the combined and in the parametric cases, we are looking at consecutive solutions for the least squares correction vector delta hat. At each step, the solution vector x hat will be updated and used as the approximate parameter vector x naught to evaluate both the misclosure vector and the design matrices. The final solution, the best estimate in least square sense, is obtained whenever the difference between consecutive values of delta hat tend to 0. In practice, meaning that such difference lies below a predefined threshold value. In the conditional adjustment case, the iteration will be based on the least squares residual vector. This vector will update the original observations, turning them into estimate observation value, L hat, which will be used to reevaluate the misclosure vector and the second design matrix at every new iteration step. The final solution, in other words, the best estimate in the square sense, will be obtained whenever the difference between consecutive values of r hat tend to 0. It is when their difference lies below a pre-specified threshold value. The following flowchart summarizes the iteration flow in the combined and in the parametric adjustment cases. It all begins with the collected observations and the choice of approximate values for the parameters x naught. Based on these approximate values of the parameters, we build the first design matrix A and the misclosure vector W, computing then the first solution delta hat. In the first iteration, we will simply add the least square solution vector delta hat to the vector x naught, obtaining the least square solution vector x hat, which will then play the role of a new approximate parameter vector x naught, being used for a new evaluation of matrices A and vector W. For every new iteration, the whole process will be repeated until the difference between consecutive values of delta hat are less than a predefined threshold value. Similarly, in the conditional case, we will use the collected observations to evaluate numerically the second design matrix B and the misclosure vector W. We will then estimate the least squares residual vector r hat and start the iterative process by computing the least squares observation vector L hat and using it to reevaluate matrix B and vector W. The process continues until the difference between consecutive values of r hat are less than a certain predefined threshold value. Let us talk now a little bit about cofactors, cofactor matrix, and the a priori variance factor. It is usual to find references to a cofactor matrix in adjustment textbooks. A cofactor matrix is simply a matrix composed of cofactors. What are cofactors? Cofactors are the ratio between variances and covariances with the a priori variance factor. Let us represent the cofactor by the letter Q, such as Q sub II equals to the variance of II over the a priori variance factor, and Qij equals to the variance of ij over the a priori variance factor. These terms Q sub ii represent the diagonal cofactors. They are written in the diagonal of the cofactor matrix. And the terms q sub ij are the off-diagonal cofactors. The cofactor matrix q, underline q, capital underline q, can then be written as q equals to the covariance matrix of the observations divided by a scalar, which is the a priori variance factor. Okay, so then the weight matrix, which is what we usually use in the adjustment computations, will be, as a matter of fact, the inverse of the cofactor matrix. In other words, it is going to be equal to the inverse of the covariance matrix of the observations, CL, multiplied or scaled by the a priori variance factor. We can then say that weights are inversely proportional to variances only when all covariances are equal to 0. The a priori variance factor plays an important role in scaling the covariance matrix of the observations with direct impact in the weight matrix. It is interesting to realize, though, that the a priori variance factor does not affect the parameter estimation process. Let us write the solution vector of the parametric case, showing explicitly the a priori variance factor. Since it is a scalar, we can multiply the whole terms in brackets, but as the first bracket is an inverse, it is divided by the a priori variance factor, therefore cancelling it from the expression. It becomes clear that no matter the value of the a priori variance factor, it plays no role in the estimation of the least squares correction vector. It is the functional model. It should be also clear from the definition of weight matrix, as we have seen before, that the a priori variance factor plays a role in the computation of the covariance matrix of the parameters, meaning it affects the stochastic model. Therefore, the a priori variance factor affects the precision of the estimates. It's important to emphasize that the knowledge of the a priori variance factor, the scale of the covariance matrix of the observations, that is very important when we perform quality control using statistical analysis. If the a priori variance factor is not known, which is something that rarely happens in practice, because in most cases it is treated as equals to 1, the only way to have any information regarding the a priori variance factor is to estimate its least squares counterpart, the a posteriori variance factor, this sigma hat naught, square naught, using the expressions given here. The sigma hat square naught equals to the quadratic form divided by the degrees of freedom. So we have the product of the transpose of the residual vector r hat t multiplied the residual vector r hat is scaled by the weight matrix, and it's divided by the degrees of freedom. As we discussed before, it is going to be either m minus u or n minus u. If the a priori variance factor is unknown, meaning the scale of the covariance matrix of the observations is unknown, the a posteriori variance factor is used to scale all covariance matrices of the estimated parameters. That's important, and we are going to talk more about the a priori variance factor and the a posteriori variance factor when we discuss quality control.